Okay, if you can take your seats, please. We're ready to begin the lecture. Okay, we are pleased to have for our first lecture of 5, Dr. Dwali. He is presently a staff member at CERN. He started his career, got his PhD at Georgia Institute of Physics and Tbilisi State University, after which was held postdoctoral research positions at CERN and also at Pisa. Later became a faculty member at ICTP in Trieste, and has been for some time before arriving at CERN, a faculty member at New York University. So he is one of the world's leading experts on physics beyond the Standard Model, and today he will begin the first of 5 lectures on that topic. Okay.
Okay, thank you very much. I think this is fine. All right, so I'm going to review some of the, well, I'll try to review as much as we can, physics beyond the Standard Model. The emphasis will be on, of course, on physics that we may discover at LHC. Now, of course, it's hard to lecture about physics beyond the Standard Model without any knowledge of field theory, but I'll try to make it self-sufficient. So, in any case, I mean, don't hesitate to stop me anytime and ask questions, and it's better that we go back and reiterate rather than you miss the point. Okay. So let me start with the introduction. So let me draw here. So what I will do, I'll be writing in real time because I have to derive some things. I'll try first transparencies. I think they work the best as far as visibility is concerned. If we have some problem, then I'll switch to Blackboard. Okay. Now, so let me. So you see the point. It's okay. So let me draw some on a logarithmic scale, some important length scales in physics. Okay, so let's say here we have the Hubble scale, something like 10 to the 28 centimeters. Then here, almost at 0, we have the so-called Planck length, which is approximately 10 to the minus 33 centimeters. Okay. And these are the largest and the shortest length scale that we are dealing with. And somewhere in between, we have a very important weak interaction scale, L weak, which is something like 10 to the minus 16 centimeters. And about an order of magnitude around it, there is a scale, which I shall call LHC, okay, which is approximately 10 to the minus 17 centimeters, okay? So now I will review, these transparencies are pretty small, but it's okay. I will review new physics beyond the Standard Model, and the accent will be on this scale, LHC. Because of the obvious reasons, because we are expecting to uncover some exciting new physics at these energy scales. This is approximately TeV energy. Corresponding energy scale is around TeV, or few TeV. And so I want to first justify this story. Okay. Now, as you know from the previous lectures about the Standard Model, at energies around. First of all, the known. All the known elementary particles and forces so far that we have discovered, they are described by the combination of 2 factors, of two ingredients. So this is Standard Model and GR, Einstein's GR, General Theory of Relativity. Okay. Now you know from the lectures, from the previous lectures on the Standard Model, that Standard Model. Well, we can sort of let me very briefly review it, okay? So I'll just take one transparency. So Standard Model we can conveniently split into several ingredients. So let me call them forces and matter. There are three forces that are subject of the Standard Model, and they are all described by the so-called gauge theories. So this is weak interaction and hypercharge. Now, so these forces they have certain similarity in nature. Why? Because the messengers that are mediating these forces, they have same spin, okay? These are spin 1, or in other words, they're vector particles, okay? So we have, here we have 8 of them. These are gluons, 8 gluons. Here we have W plus minus and Z, and the photon is a combination of this sector, as you know very well. So these are the forces. So now, as I said, they are similar because they are mediated by spin 1 particles, and because of this, they are also automatically gauge theories. Okay. Now, then we have matter. Okay, as you know, we have 3 generations of quarks and leptons. Okay, so we have let's say a left-handed quark doublet. They have so Standard Model is a so-called chiral theory, meaning that the quantum numbers, the internal gauge quantum numbers of fermions are for the left-handed, right-handed ones are different. Okay, so we have a quark doublet, a left-handed. And then we have right-handed quark singlets, okay? Let's say U and D. And we have triplication of this in 3 generations. We have similarly the leptonic doublet, E and nu, left-handed. And then we have right-handed electron. And we have, presumably at some energy scales at least, we have right-handed neutrino. Sometimes people make it part of the Standard Model, sometimes they don't, but that doesn't matter. So then, the only important ingredient which is experimentally missing so far is the so-called Higgs doublet, as you know. This Higgs, depending how you define it, it comes either with a neutral and negatively charged or neutral and positively charged components. And this Higgs doublet is very important because for 2 reasons. So first, it has to provide masses for the particles in the Standard Model, for the fermions and some of the gauge fields. Also, it is essential for restoring unitarity above certain scale. Okay, so the fact that probabilities sum up to 1. Now, so as you know, so the information about how Higgs generates fermion mass is encoded in so-called Yukawa coupling constants. Okay, so basically what you have is that the Higgs is coupled to let's say, with certain couplings, it's coupled to the and so on. Okay, so maybe there is a neutrino here. Let me write it down anyway explicitly. Okay, then it will be the same as this, nu r. Okay. So the information about the fermion masses is encoded in these Yukawa coupling constants, okay? These G's of U, D, E, and whatever, nu or whatever, okay? Now, the reason why Higgs gives mass to the fermions and to the gauge fields because it develops an expectation value in the vacuum, okay? So in other words, the Higgs field has a non-zero part in the vacuum. The way you can think about it is that the vacuum that surrounds us is filled up with literally a condensate of Higgs particles, except that these particles, they have 0 momentum and 0 energy. They have huge occupation number, okay? But they have essentially infinite wavelength. So you have this very tightly packed sea of particles in the vacuum. And this creates this condensate. In other words, the Higgs field has a classical part, which is non-zero. Okay? The way you can think about it, you can think about the analogy with, for instance, the magnetic field or an electric field. You can also think about this as a condensate of photons except the difference is that those fields would give you also a non-zero energy, always. The Higgs condensate is very special because first, it doesn't give you any energy. Okay, you can at least choose the energy to be zero. And secondly, it doesn't violate any translation or rotational invariances. Why? Because Higgs is a scalar. It has spin 0. Okay? So the reason why masses arise in this theory is because we are swimming, these particles, the fermions and the gauge fields, they are swimming in this condensate. And the masses come because of the friction. So the way you can, in other words, they move in this condensate and they scatter on it. So the way you can think in terms of Feynman diagrams is that you can think about the scattering process in which, for instance, a left-handed quark goes into a right-handed quark by scattering off the Higgs condensate. Okay. Now, of course, this amplitude of this process to scatter, the probability for a given fermion to scatter on the Higgs condensate is given by the Yukawa coupling constant. In other words, stronger is the coupling, higher is the probability of scattering, and correspondingly higher is the mass of the fermion. The same is true about gauge fields. So you can think of the scattering of gauge fields, for instance, W plus minus or Z, on a Higgs condensate. Okay? Yes?
It's starting to fall down.
Oh, yeah, that's. Ah, yeah, okay. I'll try to control it. Oh.
The projector screen is falling down.
Oh, the screen is going down. So how do I do that?
Up above, I think, just manually.
Oh, just.
Up above.
Oh, here.
The mirror.
Oh, mirrors.
Even higher.
No, there. Up. I see. Okay, very good. All right. Very good. Okay. So please remind me if this happens because I get carried on and you know. Anyway, so these are the processes. Okay. So the scattering of the fermions on the Higgs condensate. Anyway, so in other words, the expectation value of the Higgs sets the masses in the Standard Model. In particular, because it sets the masses of gauge fields of the W and Z, it sets the Fermi coupling constant. So therefore the value of the weak scale. Okay, so as I said, I mean, this is, anytime if you have a question, don't hesitate to stop me. If I don't see you, just shout from there. Okay? Yeah? Sorry? Which vertex? Which one? This one? Oh, this one. Oh, this comes from I didn't write it here because this comes from the fact that the moment I declared that the Higgs is a doublet under the SO2 group, it has to couple to the gauge fields by symmetry. So in other words, Higgs carries an analog of the electric charge, but with respect to SO2 group. And just in the same way as the charged particle shines photon, Higgs is effectively shining W and Z bosons, okay? So this vertex comes from that fact. All right? So in other words, Higgs is like a charged particle, but it's charged under W and Z. So the electrically neutral component of Higgs is charged under W and Z. So the Higgs is literally shining W and Z particles. Okay? And that's this is this vertex, literally. Okay? Very good. So okay, so this was here. So now so very good. So this is the story about the Standard Model, and so the question is, and so far there is no experimental evidence, direct experimental evidence for the deviation either from the Standard Model. There is one exception, dark matter, but I'll come back to it. So Standard Model has been measured very well, starting from this weak interaction scale, this L weak, for any distances which are larger or of order L weak. Okay. So starting from 10 to the minus 16 centimeter and farther, we don't have any experimental evidence for standard model being wrong somewhere, or any deviations of the standard model. And GR, so this is a standard model, and GR has been measured extremely well for distances, which is approximately something like 10 to the minus 2 centimeters to 10 to the 28 centimeters. Now, of course, on various length scales, the accuracy of the measurement is very different. In some cases, it's very poor, but the point is that there is no indication in these intermediate distances that there is something wrong with GR, okay, with general theory of relativity. Now, there is something funny going on in this length scale at the Hubble, because universe is accelerating, the expansion of the universe is accelerating, and this is very hard to swallow for a particle within the framework of GR for a particle physicist or a field theorist. But even that can be accommodated within GR, okay, in form of the cosmological constant. So therefore, the question is now, because we have this kind of very good agreement with the experiment so far, why to look for the any physics? Why any physics beyond the standard model? Okay. Now the reason. So I want to discuss this motivation for a moment. Okay. Now the reason for this, for looking into new physics beyond the standard model, is that standard model contains both the standard model and general theory of relativity. They contain certain mysteries. Now, in the standard model, the first one is the hierarchy problem. Okay. Then there is a so-called strong CP. In other words, we don't understand why the nuclear forces do not violate CP maximally. They don't, but we don't know why. Because they could. They had all the rights to do so. And then there are fermion masses. Okay. We don't understand the hierarchy of the hierarchy of the fermion masses is pretty mysterious, because we don't understand this replication of generations. In fact, there is no need for it. I mean, universe today would look almost the same without these three generations. There will not be some CP violation, Kobayashi-Maskawa CP violation, and things like this, but that's not essential. And then why there is this hierarchy of masses? The hierarchy of fermion masses is huge. It's like 6 orders of magnitude within the quark and lepton sector. If we talk about neutrinos, it's even larger. And so this is another mystery. Now there are also mysteries in GR. So this is the story in the standard model. So there are also mysteries in GR. Now the first one is basically it's a mystery which concerns both. It's about dark matter. Okay. With just GR and standard model, you could account for dark matter. So it will be incorrect if I say that if you could not, because dark matter could be primordial black holes, the small primordial black holes. But if you exclude this possibility, then there is some story missing there. Okay. So the mystery is about dark matter. This is essentially experimental mystery, because we know that dark matter or something that replaces it should exist because of the rotational curves of galaxies. But there are also theoretical things, okay? Now, theoretically, the point is that we know that GR is not a complete theory. Now, as you know very well, theories in physics, they have certain range of applicability, okay? Now, beyond that range of applicability, a given theory simply breaks down. It's not about question of being wrong or right. It's just limited with that domain of physical situation, okay? So for instance, let's take an example with Newton's theory of gravity. Newton's theory of gravity is a perfect theory of gravity as long as you are interested in the sources that are weakly gravitating and move slowly. Okay? So for non-relativistic source, if you want to describe motion of this kind of objects, slow objects, I don't know, cars, whatever, even the satellites, Newton's theory of gravity is a perfectly valid theory, and will continue to be so for forever. The problem with Newton's theory is that it has range of applicability. Once you want to go to the sources which are either strongly gravitating or they move fast, this theory simply breaks down. It's not about becoming wrong. It just breaks down. It's not defined there. So you have to embed this theory into a more powerful theory, which has a bigger range of applicability. So this is what Einstein's theory of general relativity does. With that theory, you can extend gravitational phenomena beyond the slow-moving objects and beyond weakly gravitating objects. So for instance, Einstein's theory of relativity can describe physics of big, large black holes, which are strongly gravitating objects. It can describe physics of extremely relativistic sources, okay, particles, and so on. Now, the point is that we know that also Einstein's general theory of relativity is incomplete. It has to be completed because it simply cannot address certain phenomena. It just breaks down. So for instance, if you want to understand what is going on near the center of a black hole, Einstein's theory just breaks down there. It's not, again, it's not a question of being wrong. It's just not applicable. So for instance, as you know very well, in Einstein's theory, when we solve for black hole solutions, the black hole solutions, at the center, they always have so-called singularity, okay? Crudely speaking, this is a region with infinite curvature and infinite densities. Now, the singularity is the way the theory tells us that it is not complete, and it has to be completed and embedded into something more powerful, which would then resolve the singularity, okay? So, in other words, so in GR, there are problems, there are theoretical problems which indicate that this theory is not complete. So for instance, there are black hole singularities, cosmological singularities, and so on, okay? So Big Bang singularity, for instance, again, the moment, every time we take the history of our universe and replay it back, within GR you end up with a singularity. With a place in space and whatever, with a moment or what you want to call it, when the theory simply breaks down, and it has to be completed by embedding into more powerful theory. Okay. So the third point is about quantum gravity. So these two issues, we believe that they are connected. In other words, we believe that whatever the correct theory of quantum gravity will also resolve singularity problems, okay? So that's why people are trying very hard within string theory framework to try to address the singularity problems of black holes and cosmological singularities, okay? So now, these facts, they indicate that GR is not complete. And so since we have these mysteries and this thing, this is the motivation for physics beyond the standard model. Now, for the central role in my lectures will be played by this guy, the hierarchy problem. Why? Because this is the problem which is essentially the only theoretical guideline we have for expecting a new physics at LHC, okay? We don't have any other theoretical indication, direct indication that there must be new physics that necessarily at LHC energies. This is the only problem we have. But this is a pretty big one, and we have to take it very seriously. Now, the thing is that this problem is related with gravity. There is a relation between this problem and gravity, and this is very important to understand. Okay? So without gravity, this problem, you could even debate it, whether it is there or not. Okay? Now, with gravity, there is no way out. So I want to explain this connection, because this is very important then for looking for the solutions for this problem, okay? And what can we expect at LHC? All right, so because it's related with gravity, let me just remind you several facts about Einstein's GR, which are important ones. I mean, they are very interesting on their own, but especially here we will need them in these lectures. I'll try to be as self-sufficient as possible and make it simpler. But now, as we mentioned, remember when we mentioned the standard model, we said that the forces in the standard model, they are mediated by spin 1 particles. Now, first of all, as you know very well, from the field theory perspective and quantum field theory perspective, the forces, they have messengers, right? We don't have any action on a distance. The way you can understand forces between the sources or particles is that they exert forces because they exchange certain messengers, okay? Now, as you know, the messenger of an electromagnetic interaction is a photon. It's a massless particle with spin 1. It's a vector. And as we said, the messengers for nuclear forces and for electroweak theory, they are also particles with spin 1. Okay? In this respect, they are very similar. Now, gravity is very special because the messenger of an interaction in gravity is a particle with a so-called graviton. Okay? Let me call it h mu nu for now on. Mu and nu are indices, okay? Which run from 0 to 3. Usual relativistic indices. And this guy has a spin 2 and mass 0, okay? And this is very important. Now, there is a fact in field theory that actually the higher is the spin of elementary particle, more restrictive is the theory, okay? To the extent that once you go above spin, for the bosons, once you go above spin 2, for instance, you start talking about a bosonic field of spin 3, etc., in field theory, you actually get problems, okay? So now, the theories of scalar is the least restrictive one, because if you have a scalar, you can write down almost any interaction you want for a scalar, okay? Then we go up in the spin. Spin 1 is more restrictive. Why? Because any theory of an elementary particle of spin 1 or higher must be a gauge theory, okay? So in other words, it automatically incorporates certain gauge principle. Now, the theories of spin 1 are also pretty restrictive. But this spin 2 has a record, because it's the most restrictive field theory that you can have of a bosonic spin, of elementary spin. It turns out that they are all possible uniqueness theorems, which I'm not going to prove here, unless you want to. But so in the sense that it's a lot of things, the moment you specify the spin 2, and you say that particle is massless, a lot of things automatically follow, okay? So in other words, it turns out that the moment you say that you want to have a theory of gravity, or whatever theory, in which the messenger of the interaction is a massless spin 2 particle, this automatically means that you are led to the Einstein's theory of general relativity, okay? There is one-to-one correspondence. So in other words, viewed as a field theory, Einstein's GR is a theory of a massless spin 2 particle, graviton, okay? So in other words, what happens is that when two objects gravitate, they exchange gravity. So, for instance, in Newtonian limit, right? Let's say we orbit around the sun, right? So the Earth is orbiting around the sun. The way you can think about it, of course, you can think about the Newtonian. There are different ways to think about it. You can think about a gravitational flux, which is exerted by a source, okay? And this gravitational flux is responsible for the Newton's law, okay? But you can also think in terms of particle physics. What is going on in terms of particle physics, the reason why we are orbiting around the sun is because we are exchanging a virtual graviton, okay? So the way you can think about it is that let's say I have a source, okay? So this is a source. And then there I have a probe, okay? And they exchange a virtual graviton. And this results into the Newton's force, okay? Now, this object is very special, this particle, graviton, because it couples to energy and momentum. Just by its structure, it cannot couple to anything else. In other words, what it couples to is the energy momentum tensor of the source and of the probe. Okay? So this is also what makes it very special. In other words, it makes it automatically a universal force. Because anything that you can have should have either energy or momentum. Usually it has both, right? But, which means that, automatically means that anything that you can imagine should gravitate. You cannot have non-gravitating objects, okay, in field theory. And this is very important because this tells you that gravity is universal. Is there a question? No. Okay. So now let's try to understand what are we. So in other words, from the point of view of somebody working in Newtonian approximation, this is simply a Newtonian force. Okay. This scattering, the fact that you scatter, is the Newtonian force. So in other words, the way you can think about it is that the source, which is heavy, okay, is producing shines gravity, literally, okay, shines gravity, and then a probe is interacting with this gravitational field. So source is creating a gravitational field, and then probe is interacting with this gravitational field. So from the point of view of a probe, when probe scatters at a given gravitational field, the scattering amplitude is proportional to the interaction between this field produced by a probe and the energy momentum tensor the field produced by the source and the energy momentum tensor of the probe. And the coupling is proportional to the Planck scale. Okay, we'll go there in a moment. So in other words, so let's say I have let me do it on different transparencies. Okay, so let's say we have a heavy gravitating object. Okay. So with an energy momentum tensor, which is so heavy non-relativistic gravitating object. Okay, so then it has an energy momentum tensor which has effectively only the mass. The rest is 0, and is localized at some point r. Okay, so it's a delta function. And then I'm probing this gravitational field produced by this guy by another probe, which is again non-relativistic, okay, which has smaller mass. And is localized somewhere else. Sorry, let me call this x. And let me call this x minus r. Okay? So this results into a Newtonian force, which you know very well. So there will be a Newtonian potential Newtonian interaction between these two sources, which is a usual story, with the mass of a source and mass of a probe, and inverse r, okay, which is inversely proportional to a distance. Now, we can compare this to a Coulomb force, for instance, between two charged objects, right? Again, the story is pretty similar at this level. Why? Because if I have a Coulomb force, first of all, Coulomb force is also electromagnetic force, is also proportional to, it's also inverse r, but it's proportional to the charges of a probe and the source, okay? So let's say E1, E2. So now we can compare what governs the strength of the interaction between this, in case of gravity and in case of electrodynamics. So for this, let me remind you that the Newton's constant, I can, by the way, I assume that since this is a particle physics school, you all know that we use units in which the speed of light is 1 and h bar is 1, right? So let me specify again, right? So units are h bar is c and it's 1, okay? Just remember forever. Now this is very convenient, as you know, because in these units, the length scale, you can measure everything either in the length scale or in the mass scale or whatever you want, okay? Because the dimensionality of the length is inverse dimensionality of the mass. Okay? So dimensionality of the length is the inverse mass dimensionality. And this is very convenient. Okay, so let me go back to this thing. So therefore, Newton's constant in these units has dimensionality of an inverse mass square. Okay? And this mass scale has a name. We call it Planck scale. So this mass scale is actually inverse of this Planck length that I said, 10 to the minus 33 centimeters. So now, using this, we can rewrite these two interactions in a more convenient way. Okay? We can rewrite them in this way. So gravity we can rewrite as gravitational potential as being proportional to m over m Planck, 1 over r, and electrodynamics also being proportional to first charge, second charge, and 1 over r. Now you see that the ratio of the masses, of course, is dimensionless, and charge in the units that we are working in is also dimensionless. So in other words, if you want to factor out this 1 over r dependence, okay, and compare the strengths of two interactions, what you have to compare is that you have to compare with the electric charge, you have to compare the ratio of the mass to the Planck mass. Okay? Now, this is very important because this immediately tells you why gravity is the weakest force we know among elementary particles. Because elementary particles are much lighter than the Planck mass. Planck mass is something like 10 to the 19 GeV, or something like 10 to the minus 4 grams. And 10 to the minus 4 grams for the elementary particle is a huge mass, right? It's a macroscopic mass. You can even weight it, right, in the lab very easily. So basically, the reason why gravity is much weaker as compared to any other forces, known forces among the elementary particles, because elementary particles are much lighter than the Planck mass. That's the reason. Notice that for elementary particle, if you had an elementary particle which is heavier than m Planck, then the story would not be the same. Okay? You could, in other words, the objects, whether it's an elementary particle or whoever, who is heavier than m Planck starts to be strongly gravitating. And this is very important. Okay? Now, we are getting to a very important point here, which is this is the reason for it. Now, so in general, right, in gravity, as we said, the analog of this, the coupling constant, which tells you information about the strength of the interaction, is the ratio typically of energy to the m Planck, right? So this is the dimensionless thing that we just derived that you have to compare to the strength of the dimensionless coupling constants of the other interactions. Now, this also tells you that the Planck scale is a cutoff of GR, of Einstein's theory of general relativity. Now, what it means that it's a cutoff? It means simply that you cannot probe distances smaller. And now this is very important. We are getting to a very important point. So in other words, in GR, you cannot probe distances less than the Planck length. This is impossible. Okay? You cannot go at the distances shorter than the Planck length. So for instance, while playing with the GR laws, okay, you cannot build a microscope which would give you the possibility to resolve distances smaller than the Planck length, smaller than 10 to the minus 33 centimeters. Okay? So in other words, Planck length is a size of a black box beyond which there is absolutely no way to go in GR. Okay? You have to complete theory by something else. Now, what is very interesting is that actually the sort of contrary to usual field theoretic intuition, on the other hand, you can go in GR while staying within GR. You can go at energies which is much larger than the Planck scale. And this sounds a bit surprising. This sounds a bit surprising because you see, usually we say that if I have to probe energy scale, if I have to probe the length scale L in general, okay, I need energies at least of order 1 over L. Already the uncertainty principle tells you that, right? So if you want to resolve what is going on at the distances of a black box of size L, you have to pump your energy in your experiment, which is at least inverse L, okay? And typically, we say, therefore, that if you cannot go at distances shorter than certain given scale, you cannot probe energies higher than that. But this is not true, because GR is an example when, it's an extraordinary example when actually this you can do. Why? And this is very important, okay? And surprisingly, this is in the core of the hierarchy problem. Now, why? Suppose I have an elementary particle, okay? And let's say I have an elementary particle of mass m, and I start gradually increasing the mass of this elementary particle, okay? So first I'm in the region when the mass of the elementary particle is much less than m Planck, and nothing special is happening. So if this particle has charge or anything else, other interactions are dominant at those distances, okay? At those energies. Now, something very interesting happens once you cross this threshold and go way above the Planck scale. In other words, if I have a source, which is any localized source, not just an elementary particle, with the mass, which is much bigger than m Planck, then this source, let's write it here, okay? This source develops a certain length scale, okay? The so-called Schwarzschild radius. What is this length scale? This length scale is or gravitational radius. Let me call it Rg. And this radius, the definition of this is that this is twice Newton's constant times the mass of the source. So this is a source of mass m. And something very interesting happens at this distance. What happens at this distance is that a particle, effectively what happens is that for any source which is larger than m Planck, much larger than m Planck, this object, this source, is no longer a small object. It becomes a big classical black hole, okay? Why? Because it creates a horizon, and no outside observer can penetrate inside this horizon and get any information and get out, okay? So in other words, for an outside observer, the elementary particle with mass much larger than the Planck scale is not anymore an elementary particle. It becomes a classical, big, fat classical object, and bigger is the mass, bigger it is, okay? It's a black hole. And this is very important because this is an extremely important property of gravity, which is not exhibited by other interactions, okay? And this tells you that, it's amazingly enough, we know very well very high energy region of GR. We don't know short distance region. But these two are different things, because at very high energies, what GR gives you back a classical gravity, as a very extremely well understood classical gravity at large distances. Okay? So, in other words, what is the, now let's try to understand what is the meaning of this distance from the point of view of a particle physicist or a field theorist or whatever. Okay? Now, first of all, this distance you can immediately derive already in the, by simply reasoning in Newtonian gravity, okay? And probably you all know this, because in Newtonian gravity you can simply ask when the escape velocity from a given object will become comparable to the speed of light, or will exceed speed of light, okay? And for that you can simply say, okay, suppose I have a gravitating source, and I'm standing on the surface of this gravitating source, and I want to take a stone and throw it away, okay? And I just want to understand what is the, what do you call it, second cosmic velocity or whatever, that the stone can leave your source. And with this, it's easy, right? You just equate the potential and kinetic energies of this object, right? So the potential energy, so if I have a source of mass m, and I have a probe of mass, let's call it something, what do you want to call it, m prime, okay? So what I have to compare is that I have to compare the potential energy, g Newton, m of source, m prime of probe, divided by r, with the kinetic energy of the probe, right? Sorry. Okay? And then this shows you that something funny is happening where the v is of order 1, okay, when the escape velocity becomes speed of light. And this immediately fixes the critical size, Rg, which is given by this, okay? So this fixes the radius. Now, of course, this is a Newtonian approximation, but it works actually extremely well, okay? Why this approximation works actually extremely well? The reason is that outside of the, even of a black hole, of a strongly gravitating object, outside of the horizon, gravity is weak. It's still weak. So Newtonian approximation is the first approximation is still okay, okay? So you can always deduce things at least order of magnitude wise. So now, so in other words, this Rg is the place where the escape velocity exceeds the speed of light. So at that point, there is no turning back, okay? After that, if you cross this, so if you cross the horizon, even in Newtonian approximation, if you cross the horizon, it's a one-way ticket to the singularity, okay? Now let's try to understand before going back to, how much time do I have? Because I don't, couple of minutes? Ah, yeah, okay, very good. All right, so in other words, from the point of view of a field theorist, okay, or a particle physicist, what is happening is this, that at this distance, at Rg, the graviton field produced by the source, okay, exceeds the Planck mass, okay? So the graviton field at this point starts being larger than the Planck mass, okay? So in other words, if we have a gravitating source and we move from infinity towards the source, we hit this point where there is a gravitational radius. A gravitational radius, from the point of a particle physicist, the way you can think about it is that the graviton produced by the source became transplanckian. Okay? This also tells you that at this point you have to do something. Now, let's come back to the hierarchy problem. But actually, it's better that I conclude, because this means that I have to cross over in the. Okay, so let me then just conclude with the following remark. It'll take half a minute, and that now again in GR. Of course, as I said, GR is a theory of a spin 2 particle, but spin 2 particle is what is this from the point of view of general theory of relativity is a perturbation of a metric. Okay, so in other words, we move in this space-time, which is defined by certain metric, and this h mu nu is a small perturbation about this metric. Now, because from all the practical purposes, our universe, for any local experiment like LHC, the background metric is Minkowskian, okay? So in our lectures, we will restrict ourselves with the Minkowski background. So in other words, the metric from the point of view of this h mu nu is the Minkowskian metric. Everybody knows what the eta mu nu is, plus a small perturbation of a spin 2 of a spin 2 particle, okay? So now, as I said, the approximation in which the metric is Minkowskian will break down when h mu nu will become transplanckian, of course, but that's a local effect. So typically, you can treat the linearized gravity in the linearized approximation or in the Newtonian limit if h mu nu is much less than m Planck. Okay. Now, to summarize, the lesson that we learned here, and now this will become very important for the hierarchy problem, is that the amazing thing about gravity, the fact is that once somebody told you that at very large distances, nature is described by Einstein's gravity, with the messenger being massless spin 2 or whatever, okay, you know that any elementary particle with mass larger than m Planck will no longer be an elementary particle, no matter what is going on in this ultraviolet region of the theory. No matter what your UV theory is, your particle which exceeds the mass Planck will start becoming a big classical black hole. So in other words, the Planck scale, you know, this is an amazing fact that you know that Planck scale is an ultimate cutoff of your theory, no matter what is going on in the ultraviolet region. And this is very special about gravity. And this is the key, about the hierarchy problem, okay? So let me finish here, and if you have any questions, of course.
get up and move around.
Yeah.
But actually, there's one difference. So if you have a spin 2 particle plus special relativity, you automatically get GR out. But you also get higher derivative operators, right?
No. Because high derivative operators automatically give you a higher.
Take that out.
Yeah. The high derivative operators automatically give you other degrees of freedom. In particular, ghosts. But,
Yeah.
So in other words, you can never write down any theory which is different from GR without introducing extra degree of freedom. And this is a very powerful statement because once you say that I only want 1 degree of freedom, you are done.
Just
so it's just GR. Yeah.
And in the equation of motion, they're restricted to 2
Absolutely.
derivatives.
You can, yeah, absolutely. If there are 2 derivatives, then you can prove that that's GR. Up to 2 derivatives, then it's GR. And this is really amazing that you can sort of prove this from bottom up.
Yeah. But can you prove that the general state
To an arbitrary high voltage.
Do you know who's proven that in a paper?
Well, I mean, I don't know if there is a specific paper, but I know that there is this method. I have done it up to like 4 when I was a student, up to like 4, because it's basically what you do iterations.
We have to start soon, but
you declare that h mu nu couples back to itself, but then it has to couple to its own t mu nu.
Right.
And this is always a guideline. So you are non-linearly completing the transformation. I'm sure this is somewhere somebody will.
right. Okay. All right. We are ready for questions. If you have a question, please raise your hand and I will run up there and give you the mic. Okay.
Hi. Beyond standard model question, why is the hierarchy problem a problem?
Go ahead and use the mic. You can share it among the speakers. Oh, no, there's a mic right there, yeah.
Hello? Yeah. So that's what I was trying to get to. But so I was preparing the basis for it. The hierarchy problem is a problem because of precisely of the fact that, you see, without GR, I will discuss this in next lecture, but it's very important. So without GR, without gravity, I agree with you. There would be at least a reasonable way to question whether there is a hierarchy problem or not, because you could always say, you know, my theory is renormalizable, it has some scale, so who cares? I mean, it has to be somewhere, so it happened to be here, okay? The problem is that once you have gravity, you know that there is an absolute regulator in your theory. And it makes absolutely no sense to run particles in the loop above the Planck mass. Because you know that simply your expansion makes no sense because the particles running in the loop with energy, even virtual ones, with energy higher than Planck, they are not particles, they are big black holes. And you cannot run elephants in the loop. I mean, you can run elephants in the loop, but the result is exponentially suppressed. So in other words, what happens is you know that the Planck scale should be an absolute regulator. Okay. So also, this is precisely the same point that you cannot have. Imagine Higgs mass could have get renormalized arbitrarily high, right? We know that it cannot be above Planck because then Higgs would, any elementary particle would stop make sense, okay? So we know that there is a regulator, and that's why there is a problem. The problem is that you know that this procedure to hide infinities and then throw them away and then restrict them within the then just say, oh, this is my physical object and I measure it. You know that makes no sense with gravity, and so that's why there's a problem because there are two scales, and because there are two scales. And the lowest scale is quadratically sensitive to the highest scale, this is precisely why there is a problem. I mean, again, the hierarchy problem is not a problem of consistency, because you could still imagine that there is some huge conspiracy at the Planck scale or at whatever, and effectively delivers a very light particle. That could still be, but look, it looks very, in the light of this, it looks very improbable. So that's why there's a problem. I'll discuss this in more details.
Okay, questions? Okay.
Okay, the question is for beyond standard model. So we know that the gravity is the matter of geometry, and how we can combine two approaches, I mean the particle physics and the geometry, I mean in the sense of the gravity.
Right, so yeah, that's an excellent question. So the thing is, that's precisely what I tried to do here when I tried to show that the way I can think about geometry, I can think about geometry of any source. I mean, when we're talking about geometry, we are talking about some sources, okay? We have sources and they create geometry, they carve space. And because most of the time we're dealing with weak curvatures, small curvatures, it makes sense to think in terms of field theory, that you have a Minkowski background, you have a source, and this source curves this background, but this carving of the background, the way you can understand it, you can understand in terms of creating virtual gravitons. And that's the whole point. So the great thing about these two pictures is that you can understand one in terms of the other. So that's the point. Now, of course, once you have curvatures which are above your cutoff of your theory, so the Planckian, the theory breaks down. Anyway, if both geometric picture breaks down, and of course field theoretic picture breaks down. So in other words, in a domain where one picture is valid, also the other one is valid. And so these two are sort of complementary languages of understanding exactly the same thing.
Okay, and how we can think about the gravity as a perturbation, because it's no more in a particle, so at the trans-Planck scale. So as you told us, it's a big Planck hole, and how to transit from the quantum point of view to the classical picture, I mean.
You mean you're asking for a black hole or for a weak source?
When our particle is not more a particle, it's a classical black hole, and how we can provide the transition from microscale where the gravity is perturbation to the...
Very good, yes, okay. So in other words, the point is this. The moment you say that your particle is much heavier than the Planck mass, then you know that this is just, you are not really dealing with it. What you are calling a particle has to do nothing with the particle. It's a big classical black hole. Now, the interesting question is precisely around the region of the Planck mass where this transition happens, okay? The Planck mass or whatever is the cutoff of your theory. So how this transition from the particle nature to the black hole nature happens? So we'll discuss this in our lectures. Yeah, so this is a very important question, of course. Because you see, that's precisely the region where we don't understand gravity, and that's where we our ideas about this transition are very important for particular for LHC, if strong gravity has to do anything with solving the hierarchy problem, for example, okay?
Okay, thank you.
What do you mean? Produce the real particle or what? Or oh, yeah, so sure. Can I put this? Oh, let me write on the blackboard. Yeah, it's much simpler. But I'll try to make it big, so for instance, right, so in the, let's make an analogy, okay? So for the gauge field, this is visible, right? So you have a gauge symmetry, for instance, for a photon, right? In which you shift photon by a derivative of some function, right? Okay? So there is a very similar gauge symmetry for spin 2, okay? In other words, the moment you say that you want to write down a theory of a massless spin 2, this is automatic. The only consistent theory you can write down, The only consistent theory you can write down of massless spin 2 will automatically have this symmetry, the following one. So this will be h mu nu plus a derivative of a vector. Okay, so in other words, the only difference is that for the spin 1, the transformation parameter is a scalar, okay, because you are taking derivative. And for spin 2, so this is spin 1. And for spin 2, this is a vector. Okay? So you can shift it by a derivative of an arbitrary vector. And this symmetry is automatic. That's the great thing about physics, that sometimes you have uniqueness things that you cannot do. Not everything goes. So here you know that if you want to write down a theory of massless spin 2, it will have this symmetry. That's an inevitability.
So how
Spinners?
Yeah, under this gauge transformation. I know the gauge would transform, but what about like a scalar?
Oh, you mean, yeah, of course. I mean, there is a consistent way to incorporate spinners and all the spins. Yeah, couple them consistently with the spin 2, etc. No, for instance, at this level, okay, at this level, all you have to do is that you form a T mu nu of your spinner or whoever, okay, and because T mu nu is conserved by construction, you know that this coupling H mu nu T mu nu will be an invariant. This will be an invariant. Why? Because this shifts by the derivative, and if T mu nu is conserved, as long as you have conserved T mu nu, this is automatically gauge invariant. So here is a prescription. Take any spin you want, construct T mu nu out of that, and couple it in this way at the linear level. At the nonlinear level, you have to incorporate higher order nonlinearities, of course. Okay?
We have a question here.
Okay, question for the first lecture. Is the path reconstruction in the detector is ambiguous or definite?
Well, it's ambiguous up to a certain level, because you always apply a hypothesis. You always have to apply a hypothesis to the data you see, and you interpret then the data you see in the context of a hypothesis, and there might be some residual mistake there. Tomorrow, for example, I will show, for example, track reconstruction or calorimeter reconstruction. Track reconstruction means that you have a certain number of hits where you apply the hypothesis that the hits have been created by a particle going through the various detectors. This hypothesis might be wrong, because it could be that the hits are just aligned by chance along a line which looks like a particle has gone through, but it could have been noise or something like this. So in that sense, there is some ambiguity involved, and in your analysis, you have to take care of that, in a sense, try to estimate what might be the related uncertainties. But it's not absolutely correct, absolutely sure what you are reconstructing. There's always an error or an uncertainty attached to it.
And when you are building the reconstruction, you assume that the path is laid by a known particle with known mass and known possible momenta, or you assume that any line...
A hypothesis always means that you have to assume something. Otherwise, if you have to assume something known. Now, known could be something which has already been measured by another experiment, or a particle which properties are predicted by a theory. Now, if a theory tells you there is a new particle with a certain mass and certain charge, for example, you can simulate what you would expect of which type of signals you would expect of such a particle in the detector. And then you could try to reconstruct a track of such a hypothetical particle and see if you get patterns, hit patterns, which are in good accordance with such a hypothesis. This you can do. For example, at LHC, for example, one will look for relatively long-lived, stable, heavy particles, which up to now have not been observed, but we can simulate how the signal should look like in a detector. So some part of the pattern recognition or the reconstruction in the LHC detectors will also look for such phenomena, such patterns. But most of the time, the standard reconstruction basically looks for patterns as expected from known particles like protons, electrons, neutrons, pions, etc.
Thank you.
I have a question about the standard model. You said that the other elementary particles are swimming in a condensate of the Higgs field. And my question is, how can you prove that the condensate is actually there?
So the question is, how can we prove that the Higgs condensate is there? I mean, that's why we need experiment to find the Higgs. I mean, what we know is that something that walks like it and talks like it is there. Why? Because we know that fermions have masses, W and Z, they have masses, and all the properties of their masses are 100% compatible with what would this Higgs picture would give you. Okay, so if there were an elementary particle, elementary field, which condenses. Now, of course, there could be other ways to accommodate. People are trying to find other ways in which they could still accommodate masses and all the masses and observables, but without actually having a single elementary Higgs field. Okay, so people are thinking in that direction. So that's why this, until we really find Higgs at the collider, we know that we cannot prove it. Now, for sure, we know that there must be either Higgs or something even more exotic, because something has to unitarize amplitudes. In other words, probabilities have to sum to 1. So, so we know that there must be some physics. If it's not Higgs, even better. Probably it would be something more exotic. But theoretically, it's almost, I mean, theoretically, I don't see any chance for having simply nothing there, and then you go on like nothing happened at high energies. That's theoretically, I don't see any way of this. But again, yes, so your question is absolutely legitimate. I mean, we have to prove that by experimentally to see elementary excitation. Now, of course, itself, Higgs may be not elementary, it may be composite. We'll discuss all these issues, okay? Then the question is, where is the compositeness scale, et cetera, et cetera.
Any questions on the CP violation? So, okay.
Sorry, it's actually a question on beyond the standard model.
Sorry.
How does an object interact with a black hole via a virtual graviton if even photons traveling at the speed of light can't be emitted?
Yes, so it's a very good question, actually. The question was, when I have a black hole, how can I talk about exchanging gravitons when, on the other hand, I told you that even photons or anything traveling at the speed of light even cannot escape from beyond the horizon. Now, the point is that so when we are talking about the gravitational force that is exerted from a black hole on any probe, that is not a real particle which is traveling continuously from the interior to outside. It's a virtual state. Okay, it's a virtual particle. Now, virtual particles, they can escape because they're virtual. So, in other words, the way you can think about it is that there is a flux, a gravitational flux. And the flux lines, they cannot break. And as long as flux lines they cannot break, they can penetrate all the way to across the horizon. So what cannot escape from beyond the horizon is any real object, any real signal or an elementary particle. So for instance, if somebody inside a black hole will try to perturb the flux, the flux lines and send a wave to you, that's impossible. You will not get it. Classically impossible. Now, as we will briefly discuss, black holes can evaporate. But again, even evaporation doesn't constitute, I mean, it's not a direct signal of something escaping from the interior of a black hole, okay?
Thank you.
All right. Okay.
Yeah, go ahead. I'm looking to see somebody else raising their hand, but go ahead.
So what would be a self-interaction term for the h mu? Would it just be like Ricci scalar or something like that?
Well, yeah, the Ricci scalar is an ultimate full Lagrange, full Einstein's action is a Ricci scalar, right? So the one that describes self-interaction of the graviton. But in the language of small perturbation that I was discussing, the graviton, you can reconstruct Ricci scalar order by order, okay? So for instance, you can find the trilinear vertex, then you can find the higher vertices, etc., okay? So you can reconstruct. Of course, at the end of the day, you will reconstruct the Ricci scalar because that's the only thing which is compatible with full nonlinear general covariance and massless spin 1 particle, massless spin 2 particle. Of course, if you have other degrees of freedom in your theory, so then you can have different other terms, but that's a different story, okay?
Okay, we have a question down here.
Yes, thank you. I've got a question on the beyond standard model. Can you imagine that basically you have the situation that the virtual particles have not a speed of the light but an infinite speed, and therefore can penetrate this region?
Yeah, I mean, virtual, yes, so it's a little bit matter of language because, let me, let's do the following thought experiment, okay? Okay, let's do the following thought experiment. So suppose you have a black hole, okay? And so let's say I have a charged particle, some Q, okay? And as you know, charged particle carries a Coulomb flux, okay? So there is a flux spreading out in all the directions, okay? Now, suppose I take this charged particle and I throw it inside a black hole, okay? So what will be the end result of this story? Now, the thing is that this black hole that I draw was pretty large, so let me draw a smaller one. So let's say here I have a black hole, okay? Okay, so now the thing is that this flux, as you know, this is something that you can measure at infinity, okay? So I can have an observer or a bunch of observers at very large distances, so let's say we are here, okay? And we can draw a big sphere around everybody, and we know that there is a finite flux corresponding to 1 unit of charge coming out of this sphere. So now, suppose now I throw this charge into a black hole, okay? Now, of course, black hole will swallow it. Let's ask what is the end result of it, okay? Do I still get an information, memory, that this charge was swallowed by a black hole? And the answer is, of course, yes. Why? Because these flux lines at infinity cannot disappear. In other words, in this case, we have hair. We are holding this charge with a hair at infinity. And so the end result of this would be, the end result I can draw somewhere else, would be that there is a black hole, okay? The metric will change slightly, and etc. And there are exactly the same flux coming out of the black hole, okay? So in other words, flux lines, now what are the flux lines? Precisely, flux lines are the example of virtual particles. You can think about the flux line as being a exchange by a virtual particle with given momenta, okay? So these are not real particles. So that's why, what we call a particle, we usually detectable particle. It's something that we detect, okay? Which is, the moment we detect it, it becomes real. So the flux can extend across the horizon. There is no problem with it. Actually, you have a flux, things like fluxes, which correspond to something that you can measure at infinity, they can extend across the horizon, okay? These are so-called, these are few things that you can characterize black holes with. And so fluxes and virtual particles are, so in this case, these are virtual. So that probably answers your question.
Okay, but I wonder, do you say here that the speed of this virtual photon is exactly the speed of light, or is has it got an infinite speed?
No, the virtual photons are not really photons, right? You can think in terms of virtual photons. They do not happen in a given time or a given place, right? They are just the way to understand the flux, right? I can think of them as virtual photons of given momenta, but no energy, zero energy, okay? So since they have zero energy, they don't, you see, flux line, there is no transmission, continuous transmission of energy between a black hole and then outside observer, right? It's just a constant flux given there. And so that's why, I mean, there's no problem, because they don't really move with any speed. It's a stationary field, which you can understand as virtual particles of zero energy.
And I can imagine you have a plus particle and a minus particle and then annihilate, and then you have no field at all?
Absolutely, yes. For instance, if I, absolutely.
Then does this field travel with the speed of light or infinite?
No, fields, of course, the maximal speed is still speed of light. There is no question about that. So let's do this experiment that you just suggested, right? So suppose I have a black hole which has a charge, and then I have somewhere another charged particle, right? Let's say this guy had a charge plus, and I have now a guy with charge minus. Now this means that I have a dipole, okay? The flux lines from the black hole, they end on this guy, right? This is the picture, right? So in other words, for the point of view of large distance observer, it doesn't make any difference whether the one charge is a black hole and the another not. It's still a dipole. Then of course, what will happen is that once you throw the other guy in, the flux eventually will disappear. The charge will disappear. Exactly in the same way if the field of a dipole disappears if you annihilate plus and minus charges. Of course, everybody, whenever there is some signal, so for instance, of course, in this way, you will know about it at infinity because there will be some electromagnetic wave traveling, right, because of dipole. Because you have created dipole and then you have destroyed the dipole. Of course, that speed will be speed of light. Everything will be normal. I mean, there are no miracles in physics, right?
Okay.
The things are still,
Thank you very much.
Okay, consistent.
Okay, I think we're going to have to leave it there today, and we'll thank the speakers again.